Starting. And today we have Joanne giving her presentation of one of the papers that she actually found the best paper of last year when we were discussing it. The best papers of the year nominees. So go ahead, Joanne.
Yep, yeah, okay, so,
Oh, click here, move it up. So you put our slides.
let's see. Okay. Yeah, guys, so, good afternoon, welcome to MLBBQ. And today I'm discussing the paper, Are Transformers Effective for Time Series Forecasting? So this paper came out in 2023, and it was AAAI's third best paper from the year. And so it kind of just sparked some discussion and some other papers about this question of, are transformers effective for this task? So we can get into that now. Oh, it's kind of light. Okay, so this is kind of the discussion around this question. So when this paper came out, it kind of just was sparking a lot of different conversations online. So when transformers were coming on the scene, they got a lot of hype when it came to time series forecasting. But I think now that we've had like a few years to kind of look at the data and the research, it's all pointers are kind of showing that transformers are overwhelmingly failing when it comes to this time series forecasting task. So this is just some things that I found online. There is this one guy who has this whole entire repository about why transformers are what you don't need. So he's just kind of collecting all of this different evidence about why transformers fail at this task. And some other papers came out kind of discussing whether or not we need deep learning models for time series forecasting. And some other interesting models, like Google put out this TS mixer model, which is an all MLB architecture for time series forecasting. And then another paper came out kind of giving good remarks on the transformer being used for this task. So yeah, and of course there were memes, and these are some of the memes that I found online discussing it. So it kind of became, it seems like a little bit of a discussion and argument. And the guys who put out the Informer paper also responded with a rebuttal paper explaining how supposedly their model is effective for time series forecasting. So yeah, we're just gonna get into the paper now and see what this group did. So this is a paper preview. Essentially the main claim of this paper is that transformers multi-head attention mechanism results in this temporal information loss, which affects this time series forecasting task in such a way that it's so detrimental that the performance is affected. So yeah, like the multi-head attention mechanism in transformer, it is inherently a permutation and variance operation, and these transformers have to use like little tricks to encode position of different tokens that they're processing. But the authors are arguing that still, even with these like encodings and different tricks that they're using, it's not still not effective enough for time series forecasting. So the models that they tested with are called LTSF-Linear. It's a set of linear models that they're using to test their hypothesis. And they tested this on 9 different data sets. And they also did some additional study into the different design elements for these new forecasting transformers to see how effective they really are at the task. And so the major conclusion that they found with their study is that the temporal modeling capabilities of transformers are exaggerated, at least for the existing long time series forecasting benchmarks. So kind of just getting into the time series forecasting problem landscape. So time series data obviously is just kind of like everywhere in our world. We work with time series data in our lab. And so, there's been a number of solutions for this long-standing task. There have been some different, statistical methods like ARIMA in the sixties, and, different machine learning approaches like gradient boosting, regression trees. And then deep learning came on the scene with, trying to apply RNNs to this problem, as well as, temporal, CNNs. And so you can kind of just explore the different approaches to this problem in this graphic. And this came from a recent, survey on deep learning, and foundation models for time series forecasting. But obviously transformers have, seen like the best, or unparalleled, performance in sequence modeling problems like NLP, speech recognition, and computer vision. So people wanted to try to apply, transformers to the problem of time series analysis. And some of the architectures that came out are log, trans, informer, pyroformer, and triformer, as well as fedformer. So this paper kind of explores these architectures as well. So, but what is the main like formulation of the time series forecasting problem? So you're just given a time series, which is containing a number of variates. And your model is trying to just predict t future time steps, given the look back window size that is determined. Oh, and Alex has a comment. Okay, there's also state space models like Mamba and the ones Eloy was presenting at something like MLBBQ. Yeah, I saw this paper as well. I wasn't able to get into it much, but I think there's been some maybe like variants of this solutions to these problems using something called state space models. I'm not sure. Does anybody have a comment on this?
I think it's just saying that they also exist.
But state space models are close to the classical models. This is linearization. I mean, they've been around since 1950s. I mean, it's a revival, but the ideas were there. So I don't know. It's kind of a combination, maybe a healthy one of classical methods with the present-based training approach. So
yeah, so essentially, we have some time series of continuous values, and we want to have a model that will try to predict future time steps, give it some kind of horizon in the future, and they use this look back window of historical data points to do this. So when our model is trying to predict more than one time step in the future, you can use something called iterated multi-step forecasting, which is also, I think, referred to as recursive multi-step forecasting. But then an alternative to this is direct multi-step forecasting. So, and I think it's kind of relevant to this paper to explain what these things are. So there's this concept called iterative multi-step forecasting, which is essentially where a model will just try to predict a new time step given their look back window of previous observations. And then with this newly predicted value, they add this into the look back window and use this new value combined with the historical points to predict a new value. So it's kind of this iterative approach. So this is the iterative multi-step forecasting, but I think this kind of approach for forecasting is prone to like error accumulation, because if they make an incorrect prediction, that is used in the look back window to make future predictions. So that's one observation that was noticed in this paper. As opposed to DMS forecasting, which means direct multi-step forecasting, this approach has a model or a series of models that just predict that only work on predicting one time step at a time. So that's two different approaches for forecasting. And so the paper kind of explores what are the differences between these two forecasting techniques. For IMS, it's an autoregressive estimation procedure. and it has smaller variance. However, it's more prone to error accumulation effects. And as opposed to this direct multi-step, it does have more accurate predictions, and it doesn't necessarily need an unbiased single-step forecaster. So just kind of getting into transformers, coming onto the scene for this time series forecasting problem. So obviously transformers have shown to perform very well on many AI tasks. And so this thus triggered a lot of research into transformers. So people also started researching how to use transformers for this time series forecasting task. So, however, the vanilla transformer has some like drawbacks that make using it right off the bat for this problem a little bit difficult. So these are some things that would have to be addressed in the architectures that come out for this problem specifically. So namely like the time and memory complexity for the problem is problematic. And and this complexity, I think, comes from the autoregressive decoder design in the vanilla transformer. And another type of transformer architecture came out for time series forecasting called Informer, which is a novel architecture for the transformer. And they worked on reducing the complexity of this autoregressive decoder design by using a DMS forecasting strategy. So, and then in the paper, they start kind of looking at different approaches of transformers and their variants for adapting to this problem. So they kind of just go through how the transformers are doing the pre-processing steps, how these transformers are doing embedding, and then adjustments made to the encoder and decoder blocks in these transformers to solve the time series forecasting problem. So specifically, in terms of the data pre-processing, it's pretty standard for this problem to use normalization with zero mean. And also, autoformer architecture applies seasonal trend decomposition behind each neural block. And then FETformer uses the same decomposition scheme as autoformer. And it uses a mixture of expert strategy to mix the trend components extracted by moving average kernels with various kernel sizes. And so that's kind of a little bit of the input embedding strategies and pre-processing. So obviously, and transformers cannot preserve the positional information of the time series, but the local positional information is what's the most important for this problem. So these architectures had to do something to address this issue. So obviously too, like the global temporal information is important, like timestamps and agnostic timestamps like holidays and events. So the state-of-the-art transformers are injecting several kinds of embeddings to the input sequence to try to preserve some kind of like ordinal information. So how they're doing this is they're doing like fixed positional encoding. They're doing this thing called channel projection embedding, and they're using these learnable temporal embeddings as well. And some other forms of embeddings that are being used is like temporal embeddings with a temporal convolutional layer, and learnable timestamps are also introduced. And part of transformer research in general is trying to improve like the self-attention schemes. Because I think the global self-attention mechanism is a quadratic complexity. So these 5 time series forecasting transformers are split into 2 categories of how they're approaching the self-attention strategies. So one branch is transformers are trying to use this sparse self-attention mechanism. And so this log transformer is using this log sparse mask which reduces the complexity to O of L log L or N log N. And then pyroformer is using this pyramid tension. And this also reduces the complexity down. And then the other branch of how to approach the complexity issue with self-attention is using the low rank property of the self-attention matrix. And so Informer is using this technique called prob-sparse attention, which also uses this self-attention distilling operation. And then FedFormer is using the Fourier transform to operate on the time series data. And so they use this Fourier enhanced block and a wavelet enhanced block with random selection. So this also reduces the time complexity as well. So in terms of the decoders, vanilla transform decoder output sequences are in an autoregressive manner. So this oftentimes slows things down a lot and also can suffer from error accumulation effects, especially for long-term predictions. So Informer is using a generative style decoder for DMS forecasting. And then Pyroformer is using this fully connected layer, concatenating spatiotemporal axes as the encoder. And then Autoformer is summing up these two refined decomposed features from Fred's cyclical component. And FedFormer is using a decomposition scheme with the proposed frequency attention block to decode the final results. So yeah, a lot of different approaches here. It's kind of just been a playground for the transformers and adapting themselves to this problem landscape.
One quick question, the colors in this last two, it's not that they're mixed and matched, it's log former is log former in all of those stages, right?
Yes, so yeah, the colors in the encoder and decoder correspond to different architectures. And like when they're
Like purple encoder cannot be used with yellow decoder, it's, or is not used in that way, it's just like the color.
Yes, yes. Okay, guys, any other questions or comments? So, well, one interesting observation that these authors made is that all of these LTSF transformers they're mainly using this DMS forecasting strategy that we explained. However, they're mainly comparing to models that are using IMS forecasting. And we know IMS is known for error accumulation effects. So the authors are hypothesizing that the main performance and improvement that were noted in these transformer papers are mainly just due to the fact that they're using DMS forecasting as opposed to IMS forecasting. So to test this hypothesis,
Just a little interjection, is that finally our reviewers didn't notice that all of those papers are not comparing apples to apples, but are doing apples to oranges.
yeah.
So basically, they're kind of like having to predict less far into the future compared to the models they're comparing against. Is that
Well, like, from what I understand, these transformer architectures are using DMS forecasting, which is like this non-recursive way to predict future time points. But then they compare it to this error-prone IMS forecasting. So that's what they used as their baseline. So it would make sense that they would see an improvement, because I think in general, if you just compare IMS to DMS, you're going to see an improvement in forecasting. So, yeah, but that's one thing that these authors noticed. So to test this hypothesis, they chose their baseline as the simplest DMS model possible, which is just a temporal linear layer that directly regresses the historical time series for future prediction using a weighted sum. So it's just a linear model that they're comparing to these transformers, and they're using the DMS forecasting strategy. So the models that they're comparing against the transformers, they're calling it LTSF-Linear, which is just a set of linear models that they're comparing to the transformers. So the first model in LTSF-Linear is this vanilla linear model, which is just a one-layer linear model. And then they're also comparing, they're using another model called D-linear, which is a model that is supposed to increase the performance capabilities of a vanilla linear model in case the data has a trend. So it's based on the strategy that's used in autoformer and fedformer. Essentially, they just decompose the data into these trend components using a moving average kernel. And then they use two one-layer linear layers and apply them to each component. And then they just sum the features to get the final result. So this figure here is just kind of explaining their D-linear model. It's a model that's supposed to perform well on data with trends. And then another model that they use in their set of linear models for comparison is called N-linear, and it handles shift. So it's supposed to improve the performance of just a vanilla linear model when there's a shift in the distribution of the data set. So how this one works is it just subtracts the input by the last value in the sequence, and it puts this through a linear layer, and then it adds the subtracted part back before the final prediction. All right, so these are some of the experimental settings that they're using. So they're testing this on 9 real life data sets. Some of them that they're testing on, I think, is the transformer temperature variation over time, traffic flow variation over time, electricity, weather, illness reports, and exchange rates fluctuation over time. And the evaluation metric that they're using are mean squared error and mean absolute error. And so the methods that they're comparing against are the fedformer Fourier transformer variance, and autoformer, informer, pyroformer, log trans. So just all the top forecasting transformers, architecture. And then they're also using this like naive DMS forecasting method, which is called repeat, which essentially just repeats the last value in the look back window as just a simple baseline.
I want to interrupt, just like one insidious thing about the peer review process, I think, is that like once like a fairly substantial number of reputable people publish bad methodologies, everybody just starts copying them and referencing them, and just like if you don't do it, everybody will like beat you on the head that you're not using the bad methodology. Like, so it's like, I don't know.
If you point something out, even if it's obvious, you get people who are like, well, it's so obvious, of course, this is what has happened to us twice. It's like, well, it's not actually contributing anything because it's so obvious.
Yeah, hindsight is very powerful, yeah. When you see the solution, it's obvious and you think you can come up with a solution. That's why many people who can read papers think they can write papers. But there is a huge gap.
Yeah, so they compare with these transformers, and then they introduce like this dummy method, which just repeats the last value in the look back window as another simple baseline. And so this is just kind of a description at the bottom of the different data sets they compare to, like how many variants, time steps, and granularity. So, okay, and this is some of their results, so we can talk about this now. So, surprisingly, in multivariate forecasting, which their linear models don't even really model correlates among variates, their linear models surpass the state-of-the-art fedformer in most cases by 20 to 50%. And with some other time series benchmarks, in linear and bilinear show the superiority to handle the distribution shift and trend seasonality features. And when it comes to univariate forecasting of the transformer temperature data sets, which are not shown here, the LTSF-Linear still consistently outperforms transformers by a large margin. And
So just a little bit about this table, up to this dual line, after the first third, all the linear models, and then all the budget transformers, right?
Mhm.
And what is the last one, repeat?
Yeah, that's the DMS strategy that just repeats the last value in the look back window. So it's like a naive forecasting strategy. It just says the future prediction is the last value in the look back window.
And then it updates the last value with actual value and moves up.
Yeah. So, yes. And so FedFormer achieves a competitive forecasting accuracy on this one data set, which is ETTH1, because FedFormer F employs the classical time series analysis techniques such as frequency processing, because they use the Fourier transform in this architecture, FedFormer F. So what these results are showing, according to these authors, is it's revealing because these their linear model, their time series forecasting transformers really don't seem effective on the existing 9 benchmarks for the time series forecasting problem. And it also shows that these linear models can be a powerful baseline for this problem. And additionally, when it comes to this repeat method, which is the naive DMS forecasting strategy, the naive repeat method had worse results for long-term seasonal data. But it surprisingly outperformed all transformer-based models on the exchange rate data set. And why is this? Well, it's mainly because it's mainly due to the wrong prediction of trends in transformer-based solutions. So it seems like transformer-based architectures struggle with capturing trends in data. And they're also thinking that transformer-based solutions may overfit towards sudden changes and noises in the training data, which results in significant accuracy degradation. But this dummy method repeat does not have this bias, so it actually outperforms transformers when it comes to this exchange rate data set.
Got a question. So I think it's figured probably to like tight for them to include error bars, but do they include error bars anywhere in the appendix or anything for these measures? I mean, the differences are also big enough that it probably doesn't play a huge difference, but just for, as long as we're talking about methodological issues, right?
Yeah, I'm not sure. I don't think so. I don't think they did.
fine.
I think another question that I have in general about this paper is that they used all of these different transformers, and I'm not sure if they fine-tuned them to the data sets that they ran them on.
That's my biggest issue with this work conceptually, is that when you take up a negative hypothesis like this, it's you have a lot more burden of proof in order to like show that this class of model doesn't work. And I don't know if they've gone through everything that I would expect this kind of analysis.
Yeah, maybe, but it could be at least interpreted as take linear models out of the box and take transformers out of the box.
Yeah, no, I agree with that.
Yeah, but it doesn't mean necessarily, maybe they've done everything that to prove. It doesn't necessarily mean that transformers cannot be made to match the
Right.
performance if,
Right.
if they haven't made the effort, but they could have, I don't know.
It's not like an incompleteness theorem where you're like, they're
Yeah,
all
yeah.
gonna,
Yeah. But it's interesting, FedFormer is the only one who is actually doing anything. So pre-trained, it's consistently better than any other transformer, right?
Yeah.
This also goes back to the point we were making, like, at the show and tell, like, basically, like, an empirical result is, like, it's not satisfying enough. You need to, like, this doesn't tell you why this is really the case, does it? I mean.
Yeah, I
just-
agree with that, but then they also start asking some questions and doing some more exploratory analysis, which I feel like kind of explores it a little bit more,
Right,
but yeah.
the theory is too hard. Sometimes you can't do good empirical experiments to kind of bridge the gap, but.
yeah.
Well, theory is almost always too hard. It's like you first, to do that too hard job, you need to convince, like, yeah, I mean, I see it's not, it is the case, but how do I prove it? It's just.
Yeah, I think that you should be able to publish an empirical paper like this without the theory as to why. But I think that also there's like a need to fill that void as soon as it's published. Like you could either fill it by like making a better transformer or coming up with a theory or whatever, but.
Well, but transformers, sorry for continuing the route, but transformers don't have to be the best model ever.
No.
I mean, they
Did
bring,
so did the original reviewers from the what is it, in the original article, who discovered this issue, did they ever reveal what exactly what data set they used for the that they tested, that they found this error on? Because it could just be the data set too. I was wondering about that.
Yeah, the authors kind of discussed that point a little bit, but yeah, I think these are just benchmarks for this problem, so that's why they chose to use these data sets. But there was also a rebuttal responding to this paper from the authors of Informer. I haven't really looked at it too much, but they basically just say, they do another empirical study and show like results. Oh, okay, our models outperformed based on the metric. So I'm not sure.
Crisis of reproducibility is gonna be huge for this debate. Everyone's gonna be finding that their thing is worse or better, or, you know.
well, the good thing about it, that the linear model part, everyone can just run for themselves.
Yeah.
And just check those numbers.
Yeah.
And
Yeah.
if Informer people don't publish their data, then it will be harder.
I'm surprised this got through, because I think if I had submitted this, a reviewer would have said,
No,
well, you obviously did something wrong, because a model this simple could not outperform these models, right?
Well, but there is an interesting observation that I didn't know about it, but I learned recently when doing some work. There are a couple of papers that have proved that, this Gaussian linear model, dynamical model, it's easy, and it tends to be people use it. It's like when derivative equals linear transformation of the value plus noise. But they have proofs akin to the central limit theorem that in multivariate cases, the nonlinear models tend to converge to the linear dynamics. So maybe in the dynamical system, those linear models are performing that well because of that. Like it's essentially becomes linear Gaussian or linear model. So I don't know, but that's interesting.
Yeah, so this is some of their qualitative results. They're kind of showing some of the graphs of performance during their testing here. So here they're plotting the prediction results on 3 selected time series data sets with these time series forecasting transformers and their linear models. So as you can see, like the transformers are failing to capture the scale and bias of the future data in the electricity and ETTH2 data sets. So it looks like they have kind of the right shape going on, but they're kind of like shifted a little bit and also like just way too big. And also they're failing to predict trends on any aperiodic data found in this exchange rate data sets.
I just can't see the colors.
Sorry.
It's not your fault, it's figures.
So they're kind of just saying like this phenomena further indicates the basically the poor performance of existing transformer-based solutions for this time series forecasting task. Okay, so another kind of like they start asking questions about transformers for this task and kind of do a little bit of investigation on these questions. So the look back window in time series forecasting is kind of an integral part of the forecasting strategy. Because it determines how much we can learn from the historical data in order to predict new data points. So it would make sense that a powerful time series forecasting model with a strong capability of extracting temporal relationships should benefit from a longer look back window. So what they wanted to do is test their linear models versus the transformer models with iteratively larger look back window sizes, because naturally, if these transformers are benefiting from, are able to extract like temporal information and dynamics from the look back window, they should benefit from a larger one. However, what they noticed is that even with the increasing window sizes, the transformer-based model's performance deteriorates or it just stays stable when the look-back window size increases. However, in contrast, their linear models are significantly boosted with the increase of the look-back window size. So that's an interesting observation that they found in this paper.
I have a question.
Yes.
Did they fine tune when they increased the window size?
I'm not sure. I heard some talk online, people kind of critiquing this paper for this reason, and I think they maybe did not, but I'm not exactly sure.
Yeah, because I'm not familiar with time series, but at least for language models, if you try to naively increase window size, performance just continually deteriorates because the embeddings for the rotational embeddings aren't suited when you increase or if you change the window size. Yeah.
How old is this paper?
It's from 2022.
Okay, so I'm gonna like play like a little bit devil's advocate here, and I kind of think in some ways this kind of tells you where you could get low hanging fruit papers. But no, you know, like,
I just think it's a gamble, because we've tried it and just
No,
rejected because it's
exactly.
low hanging fruit.
so you don't think you could make a better time series forecasting transformer?
Oh, sorry, I interrupted you before you could finish your thought, go ahead.
No, I'm basically saying that, like, I mean, if all of the time series transformers are doing badly, that means that you could probably make a better one. Like, they're not achieving Bayes optimal error and like the, like. I don't know.
No, but like, let me reinterpret what
Yeah.
you're saying. Like be a devil's advocate of a devil's advocate, like a second order. Basically, you're succumbing to the lemmings, to the crowd. It's like all lemmings are accepting that transformers are the best one. We need to prove them that they are by making
No,
yet
no,
a better transformer.
I'm
So
just
that's
like a little bit cynical, like,
Yeah, like linear models are best.
to some extent,
That's-
a lot of reviewers have kind of followed the hype train and
Yeah,
are
well,
infected
we
by the
all-
hype train. And I'm a little bit pessimistic about human nature. I don't really think that you can really like convince people like this of like something too terribly novel, but you can lead them like incrementally away from something really stupid. So that like that's, yeah.
It's just like the phrasing, we should put it on the wall. It's like you can lead people incrementally away from something really stupid. Yeah, that's like well said. I'm not sure, but when I was introduced to science from books, just truth is better than being right.
Oh, yeah, I mean,
It's
in the absolute sense of the word, but then getting people to accept truth, the history of like really novel ideas is often getting like really attacked at first.
Yes.
And then like in the physics community, they used to think that like physics grows at the speed of like the generation dying off that learned last like generations.
Yeah, science progresses one funeral at a time.
Yeah.
Yeah,
So-
but the point is that the task of convincing crowd is a task of marketologist, a different personality from a scientist whose task is to get to the truth.
Yeah, but come on, don't you think that you have to be, you admit, there's a little bit of marketology in the names that you choose for your papers, the presentation of your paper.
Yes, you have to
The
be to
grants that
survive.
you write, the people you network with, blah, blah, blah. It's all, there's a whole lot of non, like Zen level truth that has to go into getting an idea into it.
But if you're getting good at something, you're getting bad at something else.
Yeah, that's true.
So like, where do you want to put your soul to? Because you're dividing.
I would enjoy making an incrementally better transformer. I mean, I'm not.
Okay, well, we got to the truth. Go ahead, let's do it.
Hey, you gotta compare this to my previous life when like web development, JavaScript like, in like the worst possible ways from like. 20
Mohammed, close your ears.
no, I mean, Muhammad stuff is really cool, like, I'm talking about like 20-year-old dead systems in industry that people have to work on.
And you can make
Like-
incrementally better reacts.
Like getting people to use 10-year-old technology in like the DC technology industry is like literally an act of Congress, so it's like.
We have 15 minutes left. I don't know, John, do you have more slides? But
Yeah.
it's a good discussion. That's why we're here. Yeah.
It is a good discussion.
Okay, so they also asked the question, what can be learned for long-term forecasting? So they wanted to test like how well these transformers perform for like farther horizons of forecasting. So they tested two different look-back window sizes, they tested two different look-back windows and with the same look-back window size. So the close one has a smaller forecast length and the far one has a larger forecast length. So it looks like, oh yeah, and what they think in terms of the short-term forecasting strategy is that it's all about learning the temporal dynamics in the look-back window, and that will help a model perform better when it comes to short-term forecasting. As opposed to long-term forecasting, they're hypothesizing that it's more about how a model can capture trend and the period of the data. And that means the farther the forecasting horizon is, the less impact is in the look-back window. And what they found is that these transformers are basically not performing very well for the farther forecasting. And the takeaway is that the existing solutions tend to overfit temporal noises instead of extracting temporal information if given a longer sequence. So it's kind of indicating that these transformers are only capturing similar temporal information from the adjacent time series sequences. Because capturing the intrinsic characteristics of the data set generally is not requiring a lot of parameters. So like just capturing the trend or the period of data can only require like 1 or 2 parameters, which is causing these transformers to overfit because they have more parameters for this. So this is kind of explaining, they're saying why their linear models are performing better than transformer-based models on this task as well. So then they bring into question, how effective are these self-attention schemes for this task? And so what they did was they took this informer model and they gradually just stripped away all of these additional design elements that were added to this model to address the self-attention scheme. And so they replaced all the self-attention layers with linear layers, and they discarded some of the other auxiliary design, which left only the embedding and linear layers. And they basically just simplified this to a 1-layer linear model. And what they found was that the informer, which is a state-of-the-art forecasting transformer, performance was increasing as they were simplifying the model as well. So another question that they asked is, how well can transformers preserve temporal order? So can they preserve the temporal order well, which is arguably the most important aspect of time series forecasting. And so what they did, again, is they're looking at, they started taking away the different positional clues that are used in these transformers. Like some of them are using positional embeddings, so they stripped those away, and they saw that the forecasting errors were increasing in the transformer models. And some models are using timestamps, and so they removed from the models that use timestamps, they removed those and also saw that the performance was decreasing as the forecasting lengths were increasing. And they used a single time step for each token. And so since a lot of these models use a single time step for each token, the temporal information in tokens is required. So as they started stripping these away, they were seeing that the performance was declining rapidly in models like AutoFormer as they started losing the global temporal information. However, FedFormer was suffering less because this variant that they were looking at uses the Fourier transform data. So it kind of helped them a little bit in that regard. Yeah. Okay, actually, I think I explained maybe this slide. Okay, this is the slide that I just explained, but an interesting thing that they did. To test how well the positional encoding works for these transformers. Is they took the data set and they shuffled it randomly, and they wanted to test how well the transformers perform. And so what they noticed was that obviously in the linear models, the performance was really severely impacted because the temporal information was lost when they shuffled the data set. But the transformer performance was not really affected that much, even after the shuffling. So they're kind of concluding that the transformer models are not really preserving the temporal ordering information very well, even with the positional encoding and other embedding strategies.
Yeah, it's interesting for Pavel's work and a discussion that Noah and Pavel had at this talk when Pavel spoke at the 1 p.m.
Yeah. Yes, so, okay, and then someone might say, well, what if we try the transformer on a big data set? So obviously the data sets they tested them on are not that big, so they performed a study kind of comparing that and looking into that. And so, someone might say the poor performance is due to the small sizes of the benchmark data sets. Because unlike computer vision and NLP, time series forecasting is performed on collected time series, so it's difficult to scale up the training data size. And obviously the size of the training data has a significant impact on the performance. So they did some experiments on this traffic data set where they trained a model on the full data set, and this one is called ORI. And then they trained a model on a shortened data set, and it's called short. And so the result is that the prediction errors with reduced training data are lower in most cases. And why is that? Because a whole year data probably has more clear temporal features as opposed to longer but incomplete data size. So the training data scale, as they're concluding, is not a limiting reason for auto-informer and PET-former performances. And then one of the biggest motivations for exploring like new transformer architectures, why do we need to keep like changing the existing transformers, is because they're claiming that the vanilla transformer has this quadratic complexity, which is too high for this time series forecasting task. And
Well, it's too complex for just about every task, really. Nobody uses vanilla transformers for really anything for that.
Wait. My information is vanilla transformer is the only thing that works. All the other modifications are not really used because they don't make any difference. Yeah, the vanilla transformer is the most powerful transformer ever. All the rest are just publication.
Okay, well.
That's what I heard. Yeah, the modifications don't really work and don't add anything.
So it's just like.
Maybe for time series there is a special case, but
Okay, yeah, well, that's interesting.
for the long context, I'm hearing this autoregressiveness, which we knew from OSTM, is good. But yeah,
That doesn't seem to play out in the MRI literature at all. But like in the medical imagery, like swim transformer and swim unit or swim unit are pretty much top of the line.
yeah. But
Also, I'm a bit surprised by you saying that as well, because I've definitely seen like individual architectures on specific problems outperform vanilla architectures, but
And what about like the GPTs? Are they vanilla transformers?
yeah, but what I'm hearing is yes, like GPTs are
I think they need like more data than like.
yeah, more data, but they're just like more efficient to train.
But they're like more broad, like they have broad representation.
That's what I'm hearing.
So I didn't hear the answer. Sorry, I don't study LLMs that much. So like are the BERTs and the GPT-3s, are they like vanilla transformer?
They're half the transformer. They use the.
Yeah, only a part of it.
Okay, so they don't have any like complexity saving like modules in them at all.
Parallelization, lots of hardware, efficient implementation to shuffle the data.
They probably also have like mixture of experts that do.
Yeah.
Well, in some sense, I mean, like that's I mean, the swim transformer is trying to preserve self-attention, but it does kind of like make windows in such a way that it reduces the complexity.
I think like they kind of need the local focus that they have with CNNs. That's why with swing transformers, you need much less visual data. But with VITs, that is the counterpart for swing for like the global transformers. You would need more data because they don't have like local focus like CNNs do, which is like more suitable for images. That's why you would need like fewer data set with swing. But with VIT, given enough data, you would outperform swing transformers if you have like enough data, because they need more data to focus on all the patterns, learn the representations.
Then they have more parameters. So
think
inductive
so.
bias, it's kind of the inductive bias question.
Yeah, it's because if you have like narrower inductive bias for the task that you are solving, I think you need less data probably.
Yes, for proper inductive bias, you don't need as much data. It's a trade-off. Okay, yeah, maybe we can conclude.
Yeah,
So-
sorry,
No,
yeah,
no.
there was a lot, they were kind of just exploring a lot of different questions here, so. Yeah, so they're claiming, they need to keep adding to transformers, and they were able to prove that they were, to improve the theoretical complexity. However, it was really unclear, as to whether the actual cost on the devices improved. And, they don't really understand why the memory issue is so unacceptable for today's GPU devices.
What do you mean, what do you mean the memory issue? I'm looking at the table, so there is, the memory is 10 times larger for transformers. But the parameter number is 1,000 times larger for transformers, the number of parameters.
Yeah, I think they're basically saying like, transformers are not really out for like, if you look at FedFormer, the MACs is much bigger than the vanilla transformer, which doesn't really make sense. They're trying to address the complexity issue. And then also FedFormer has a lot more parameters than the vanilla transformer, and they don't do that much better on time, and they also don't do better, well, they do slightly better on memory than the vanilla transformer, but yeah, they're just kind of showing like most transformer variants incur similar or worse time and inference time and parameters in practice than a vanilla transformer. But yeah. Yeah, and then they just did some other comparisons with univariate forecasting. This is just the distribution of the different data sets. And then they visualize the weights of their linear models on the different data sets.
Oh, toplet structure.
Yeah.
So it's tracking like a other correlation that is falling off.
And then they showed like the full results here of different look back window sizes, but oh, sorry. I don't know why I'm still touching. But yeah, I think I'm not sure how I feel. I think there's some definitely arguments for both sides.
Well, yeah, coming back to this both sides thing, I think as long as we all intellectually honest and continue the dialogue, we can overcome this tendency of herd mentality that we are a herd animal. But yeah, it's like back to your comment about really hard to overcome. But as long as we in science maintain scientific culture of honest, intellectually honest arguments, then we can be better than normal crowd in high school.
Yes,
I think
but I
we
want
need
to
some-
devil's advocate, your devil's advocate. Or devil's advocate.
How many layers?
And
do you
say, that
Well,
I think
I don't know.
it's to and fro, I think it's to and fro, so like, there's times when it's good to go with the crowd. It's kind of a low energy situation when you don't know what to do,
Yeah.
but if you spot the low hanging fruit that the crowd's not seeing, that's your opportunity in life. So,
Yes, but then sometimes you get flack when people are like, Oh, it's so low.
Or,
Yeah.
well, anyways,
I
but
think we
then,
need
then
to-
if you end up with a situation where you only pick up the low hanging fruits of the specific kind that.
Yeah, sure.
It's it, it's just like, and there's this whole quantum computer in your pocket laying on the side of the road, but you won't be able to see it because like, we are working that out of it.
That's very true.
Well,
So I think what I mean, my struggle with research lately has just been not getting frustrated when it doesn't go through. And it's like, I think we need strategies as individuals, at least I need to psychologically
Yes,
deal
yes,
with the
yes.
frustration.
Well, we can talk about this offline, so we don't leave this to other people. We have some strategies, but we don't want to reveal on YouTube yet. Thank you, Joanne. This is great and a lot of information. And also, yeah, it's back to the history of science and what we're all doing here. I think it's a good dialogue in the community. Instead of like, yeah, the most popular model is the best. It's like, do they really work this? If they put error bars on. Don't forget, in the next door, there is a talk right now. Try institutional center, try student talk. So please join us in a bit. So do you want to show the parting final slide and?
Yeah, this is the final slide. I wanted to add kind of this discussion slide, but.
Oh, we had, yeah, you can treat, you spurred the discussion.
But yeah, I think it would be interesting to see like a follow-up maybe of someone kind of playing the other side of the argument, kind of looking into the rebuttal papers and things like that, so. Yeah, it would have been nice to look into that, but this paper was kind of a lot.
Oh, yeah, one more comment, William, if you want to do it. So the thing is like, it's not to make a better transformer, but to take the best of all worlds. If you see there's something good in that community, how to combine those solutions.
Yeah, I think
Thanks everyone for joining.
a lot of convergence. So. Tomorrow.